Okay, here we go. It's rational numbers. Let's define our terms. The vocabulary is so important in math. It's a thing that's kind of overlooked. It's important to have the vocabulary so that each year you do this, your knowledge can come back. It's easier for your brain to then access that knowledge. So looking at rational numbers, let's just define what rational numbers is. What we notice in the base of that word is the word ratio here. The word ratio is important because that word ratio tells us what we're working with here. It is numbers that can be written as a comparison of two integers, or integers as we usually say. Usually what that means is that we can say that any number over another number set up as a fraction is an integer, is a rational number, but this is only true as long as b does not equal 0. Just a reminder, because if b equals 0, like for instance, if we had 4 divided by 0, how many zeros are there in 4? We can't define how many zeros there are in 4, so that's impossible, which we would just then say is undefined. Boop. So in order to remember like kind of what integers are, so let's look at the number system itself. So the number system is important, especially in how we talk to each other. So what we start with in the middle here is, I'm going to skip over natural numbers. We're going to say whole numbers in here. And whole numbers, when we talk about whole numbers, we're talking about all those kindergarten, first, second, even third grade numbers. Those whole numbers, no pieces of those numbers, 0, 1, 2, 3 going off into forever. Once we take a step outside of that circle, we have the integers, I-N-T-E-G-E-R-S. Now the integers are all the whole numbers, so they're included in the integers, and then their opposites too. So the integers bring in the opposites of the whole numbers, which is like -1, -2, -3. Now, just as a reminder, I wrote that in reverse order, right? On your number line, what you want to see is -1, -2, -3. That goes off to the left. Then beyond integers, within the integer set, we have rational numbers. Now, rational numbers are anything we can write as a fraction. Can we write 1 as a fraction? Of course, 1 over 1. Could we write 3 as a fraction? 3 over 1. That's why whole numbers are included in rational numbers, but not all rational numbers are whole numbers. How about an integer? Could we write -71 as a fraction? Of course, -71 over 1. But for rational numbers specifically, what we're looking for is a comparison of two numbers that are integers. So 3/7, that's an integer. That's a rational number because it's a comparison of two integers. Boop, boop. Or 0.75, which we could write as 75 over 100, a fraction, 75 over 100, which is the same as 3/4. Or -7/8, which is a comparison again of two integers, which forms a rational number. Let's talk about examples of rational numbers. Remember, rational numbers are a comparison of two integers. Comparison of two integers. Set up as a ratio, which means we should be able to write a rational number as a fraction. Let's go to the blue. Or a decimal. So let's get some examples. So first example, let's talk about percents. If I had 19%, that is the same as 19 hundredths, or 19 hundredths. That works out. How about as a decimal? We can write them as a decimal, D-E-C-I-M-A-L. So if I had 0.75, hopefully you remember that that is the equivalent of 3/4. I can write them as a fraction. So let's do 5/6, which is equivalent to 0.83 repeating. And I can write them as a, let's go back to black here, as a mixed number. So let's say 3 1/5 is the same as, let's see, 3 times 15 plus 1 is 16/5, which is the same as 3.2. All right, now let's look at converting decimals to fractions and fractions to decimals. So taking rational numbers and being able to move them from either form. So sometimes on occasion we want to put them in a place where it's easier for us to work with. So let's look at how to do that now. What we see when we see a fraction is we see division, right? This literally says 7 divided by 8. And when we write that, remember the key for this is that 7 is going inside that division bracket. So it's 7 divided by 8. It goes a little bit opposite in how we read, but that's okay. You can handle it. Just remember, I think the acronym that I remember from 6th grade would be NEDO, which is the numerator goes inside, the denominator goes outside, and 0, 0, 0, just to get us started. So how many 8s go into 7? 0. I put my decimal there to remind myself there's a decimal. How many 8s in 70? There's 8 of them, so that's 64. 6 remaining. How many 8s in 60? 7 of those. So that's 56. 4, let's bring that 0 down here. 5 gives us 0. So what we found was the decimal equivalent for 7/8 is 0.875. All right, let's try this one. Now, for the mixed number, there's two ways to do this. One, we could take this and turn it into an improper fraction and then do the division. I'm not going to do that, though, because one of the things that I hope you're aware of now is that we can take that -2. That -2 is just going to be the start of our answer. Right? Nothing's going to happen with the -2. But we need the decimal portion of it. So let's bring that 2/3 down here. So remember, numerator inside 2 divided by 3. And let's put our dot and our dot, because there are 0 3s and 2. And then let's annex a 0 here and say 6, 18, 2. All right, let's see what happens here. Let's annex another 0, 6, 18, 2. All right, so in this case, we have what we describe as a repeating decimal. You can see a pattern here. Each time I'm going to take away 18 from that 20, and I'm going to have 2 remaining, which is going to then convert back to that 20. So in that, we just have a repeating decimal, and then what we'll do is we'll see how does it repeat. It repeats with one digit, just 6, 6, 6, 6, 6. So we're going to say -2.6, and then we're going to use bar notation, and the bar notation is like that. And that tells the reader that this number was -2.6, and then the 6 goes on forever, and there's nothing we can do about that. Our last one here, we're going from a decimal to a fraction. So if you remember, just read it out loud first. Now this is where place value matters. We've got tenths, hundredths, if you remember your progression, then tenths, hundredths, thousandths, 10,000th, 100,000ths, you get the idea. Here we're going 45, not tenths, but 45 hundredths. And if we're saying hundredths, that means that that 45 is 45 over 100. Now, what we love in math is simplified fractions. Improper is okay. Maybe your teacher wants you to always put it into a mixed number, that's fine. But improper is all right as long as it's simplified. For this, let's simplify this. Most people are going to say greatest common factor. I kind of just look for what will work for me and then kind of break it down into smaller pieces. I got a number that ends in a 5, and a number that ends in 0. I'm going to divide them both by 5. So 45 divided by 5 is 9. 100 divided by 5 is 20. And now we ask ourselves, 9 and 20, do those have a common factor? 1, 3, 9. 1, 4, 5, 1, 2, 4, 5, 10, 20. No. No common factor, which means that's our answer. So 45 hundredths is the equivalent of 9 twentieths. This came up in our example problems, but I thought we'd show this now because this is a special case. When we're converting fractions to decimals and decimals to fractions, we've got a pretty standard algorithm. That's if we're in fractions, we're dividing by the denominator, the numerator by the denominator. When we're in a decimal form, then we're just converting it to its denominator over the place value of the fraction. Here, though, we have a repeating decimal. So we have a number here with 0.4, and then 4 goes on forever. So the way to handle this is we don't have an actual place value that we can use for the denominator. So we kind of have to create one. So let's create one like this. Let's say I just want the number n, or the variable n, to be equal to 0.4 repeating. You know, don't forget, now that is 0.444444, and I put an ellipse on there because the 4's keep going. I don't have enough whiteboard to write all the 4's. All right, so if I say that, now I'm going to use some algebra here. Let's bring this in. I'm going to multiply both sides by 10. So I'm going to say 10 times n and 10 times 0.4 repeating. And that's going to give me 10n is equal to, okay, so that one of those 4's comes out, and now I have 4.4 repeating. Now, we have to go back and look at what this is. If I go back to this spot right here, n is equivalent to 0.4 repeating. Now, because of that, what I'm going to do down here is I'm going to subtract n from this side, and I'm going to subtract the equivalent of n from that side. So if I subtract n from here, and I say minus n, so I have 10 n's, and I want to take away one of those n's. That's going to leave me 9n. Now, on this side, though, I'm taking away the equivalent of n, which is 0.4 repeating. Now, when I take away that 0.4 repeating, what am I left with over here? That 0.4 repeating, those all become zeros, and what I'm left with is just 4. All right, now I've got a one-step equation. And to solve now for this, I want to say that I'm going to divide that by 9, divide that by 9, and I get n equals 4/9. And that is the fractional equivalent of 0.4 repeating. Now, this is great. Here's the proof of this. But the reality of this is that anything that I work with that has a repeating decimal will have a denominator that is a series of 9's. So if I had 0.2 repeating, that is 2/9. If I had 0.71 repeating, now that means it goes 7-1, 7-1, 7-1, 7-1, 7-1. The equivalent of that needs an equivalent number of 9's. So 71/99, right? The repetition, the sequence of repetitions is 2 digits, so I need 2 digits in my denominator. The repetition here is 1 digit, so I need 1 digit in my denominator. So if I said 0.397 repeating, I would have 397 over 999. Now, you know and I know that the most important thing with fractions is simplified fractions. So each of these we take a look at and say, can we make it smaller? Can we make it simpler? 71 over 99, they don't have a common factor. 397 over 999, I'm going to leave that up to you. See if you can figure that out. You know that the test case for threes, right? If a 3 is a factor, we can add the digits together, and if that sum is divisible by 3, then you're great. 999 divisible by 3. 3 plus 9 is 12, plus 7 is 19. 19 is not divisible by 3. They do not share the common factor of 3. Okay, vocab time. So we've got rational numbers, right? So those are a comparison of two integers. We've got a over b, where b cannot equal 0. We've got terminating decimals. Which is something like 0.75. That has an end. We have repeating decimals, which is like 0.3 repeating. We have bar notation, which is that thing right there, that bar. And don't forget things like numerator and denominator, fraction, decimal, mixed number, percent. You know what an integer is? An integer is all the whole numbers and their opposites. Those things matter, especially in the conversations that we have about math.